Hi students, welcome to my lectures on thermodynamics. In the last class, we have discussed about how to find enthalpy of reaction using heat of formation data. In today's class, we are going to discuss about finding of enthalpy of reaction using heat of combustion data. Because sometimes heat of formation data will be available and sometimes the heat of combustion data will be available. So let us use an example. We will understand how to find out the enthalpy of a reaction using combustion data. So let us, for example, 4 moles of carbon in the solid phase is reacting with 5 moles of hydrogen in the gas phase to form C4H10. This is the reaction. Assume this reaction is happening at 25 degrees centigrade to 98.15 Kelvin. For this particular reaction at this temperature, we have to find out the enthalpy of this particular reaction. The data available to find out this enthalpy of this particular reaction is in the form of heat of combustion data. The heat of combustion is nothing but how every reactant is reacting with oxygen. Combustion means any carbon molecules or any molecules reacting with oxygen to form the products. So if we can see, to find out this heat of reaction data, I have to find out how carbon is reacting with oxygen and how hydrogen is reacting with oxygen and how C4H10 molecule is reacting with oxygen. Once I have the heat of combustion data of carbon, hydrogen and C4H10, we can able to find out the enthalpy of reaction. Let us proceed. I know from the heat of combustion data, carbon plus oxygen will react to form CO2. This is the first combustion data with respect to the carbon. And what is second element we are required is hydrogen. How hydrogen is reacting with oxygen to form water. So this is the heat of combustion data of hydrogen. Similarly, how my C4H10 is reacting with oxygen to form carbon dioxide and water molecules. So our interest is carbon, hydrogen and C4H10. So all the carbon is there in the first reaction, hydrogen is there in the second reaction and C4H10 is there in the third reaction. I know heat of combustion data of first reaction, heat of combustion data of the second reaction, heat of combustion data in the third reaction. And if you can observe, carbon and hydrogen are in the left hand side, C4H10 is in the right hand side. If you observe these two reactions, of course the carbon is on the left hand side, hydrogen is also in the left hand side. But C4H10 is also in the left hand side in this particular reaction. But in our reaction, C4H10 is in the right hand side. So somehow we have to get C4H10 on the right hand side. I know the forward reaction. Okay. In the backward reaction, that means 5 moles of water molecule plus 4 moles of carbon dioxide to form C4H10 and 6.5 moles of O2. This is a reverse reaction. If my forward reaction heat of combustion is negative, the reverse reaction will be in the positive. Okay, this is how we have to deal according to the position of our reactants in the reaction. Carbon, hydrogen should be on the left hand side, C4H10 should be on the right hand side. So now I have the 3 reactions. Using this 3 reaction combustion data, I can able to find out my enthalpy of the reaction. See, in the first reaction, how many moles of carbon is required? 4 moles. But I have here only 1 mole. So let us multiply the first reaction with 4. That is why 1 into 4. In hydrogen case, in this particular reaction, I need to have the 5 moles of hydrogen. But here it is only 1 mole of hydrogen is there. So multiply the second reaction with 5 so that I can get 5 moles of hydrogen. Similarly, in the third reaction, in this main reaction, I have only 1 mole of C4H10 is required. So in this third reaction, I already have 1 mole of C4H10. I don't need to multiply the third reaction with any multiplier. So first reaction will be multiplied by 4. Second reaction is multiplied by 5. Third reaction is multiplied by 1. That means nothing. Okay, that means same reaction will come. So if I multiply the first reaction with 4 moles of carbon, 4 moles of oxygen to form 4 moles of CO2. Similarly, the enthalpy of this first reaction should also be multiplied by 4. So 4 moles of delta H of first reaction at a standard state. I told you the degree representing 1 bar pressure. So I got the first reaction. Here I got the 4 moles of carbon. That's fine. In the second reaction, I have multiplied by 5. So 5 moles of hydrogen and 5.5 moles of O2 and 5 moles of water and 5 times this total enthalpy of this reaction. So I got the second reaction. Similarly, third reaction I have written down as it is. Now sum up. I have the 3 reactions which is required to find out the enthalpy of this particular reaction. Now you can see the things automatically cancels out. 4 moles of oxygen is here. Okay, and on left hand side 4 moles of oxygen. On the right hand side also, if I 4 moles of oxygen plus 5.5 moles of oxygen on the left hand side. On the right hand side 6.5 moles of oxygen. So these both cancels out. Similarly, 4 moles of carbon dioxide is on the left hand side and 4 moles of carbon dioxide is also on the right hand side and left hand side. So these two cancels out. If you talk water, how many water molecule is there? On the left hand side is 5 moles of water, on the right hand side is the 5 moles of water. So these both cancels out. So if you sum up, oxygen will cancel out, water will cancel out, okay, and CO2 will cancel out. So the remaining is 4 moles of carbon, 5 moles of hydrogen gives rise to 1 mole of C4H10. Now whatever the enthalpy reaction is required, you are getting by adding these 3 reactions. So similarly, you have to add the enthalpy of all these reactions. You can see enthalpy, add, sum it up. So minus 157406 minus 1429150 plus 2877393. If I sum up these two, the enthalpy of this particular reaction is minus 125790. Okay, that means enthalpy of this reaction is nothing but minus 125790 joules. So we have found it using finding enthalpy of reaction using heat of combustion data. So what is this minus 125590 joules? That means if you see here, every 4 moles of carbon is getting reacted, this much amount of energy is evolved. In other way, every 5 moles of hydrogen is getting reacted, this much of energy is released. That means every 1 mole of C4H10 is formed, this much of energy is released. So the same thing I have represented here. Minus 125790 divided by 4 moles of carbon in the solid state is nothing but 31447.5 joules of energy per every mole of carbon is reacting in this reaction. Similarly, minus 125790 per every 5 moles of hydrogen gas is getting reacted in this reaction. That means minus 25150 joule per every 1 mole. That means if I divide it by 5, I get minus 25150. That means per every 1 mole of hydrogen is getting reacted, this much amount of energy is getting released. Minus 125790 by every 1 mole of C4H10 is formed. That means minus 125790 joule per mole of C4H10 is forming in this reaction. That is how we have to represent this total energy in the form of individual components in the reaction. I hope this simple example illustrates, explains how to find out the enthalpy of reaction using heat of combustion data. Imagine, just keep it in mind that whatever we have done here at a temperature of 298.15 Kelvin. So inbuilt, whatever the enthalpies are representing here, which is at a temperature of 298.15 Kelvin at degree, standard heat of reaction degree representing 1 bar, pressure is 1 bar. So let us meet with the new lecture. Thank you very much.